I'm Craig Lawless.
I'm Kevin Garcia King.
And this is Sounds Like Infrastructure. In 2013, a white paper that aimed to revolutionize transport appeared on the internet. And this white paper came in two parts. First, there was the non-technical part, about 5 pages long, a sort of summary of the idea.
Then there was the other part, 53 pages long, full of technical specifications like expected pressure, onboard power, propulsion.
And then there was speed. The new system said it could move people from LA to San Francisco in just 35 minutes. The paper had been published by Elon Musk, who had sat down with some SpaceX and Tesla engineers to flesh out the idea for what they called Hyperloop.
I think what that paper also really did was let the world know that all of the technology elements which are needed to make a feasible and viable Hyperloop system are here with us today.
The idea went something like this. Step 1, put passengers in a pod. Step 2, put that pod in a partial vacuum. And step 3, move that pod in the vacuum over air casters, which are basically the same tech used to keep the puck off an air hockey table.
People thought the white paper would come with the news that Musk was launching a new company, but surprisingly, it didn't. Instead, he made the idea and research open source. By doing that, he had left a tantalizing engineering challenge. And if there's one thing engineers love, it's a challenge. Engineers like Chris.
I'm Chris Bobko, Chief Engineering Officer at Hyperloop TT.
Chris and Hyperloop TT saw Elon Musk's paper and said, "We think we can build this thing." And Ferrovial are now collaborating with Hyperloop TT to try and figure out all the different aspects of how this new mode of transport could work.
When we're saying it's a new mode of transportation, I think that's really setting the stage of, yes, we're really inventing something, putting all of the ingredients together that have not ever been put together in this way before.
Because the unusual thing about Hyperloop is that even though it seems like something from a sci-fi movie, all the ingredients, basically the technology needed to make it, they already exist.
The Hyperloop pods, for example, they are using fiberglass and carbon fiber.
That's Adrian Talbot, the head of Ferrovial's Center for Excellence.
But in between the carbon fiber inner and outer shells, you have fiber optic cable for sensing to allow us to, provide information about its status, its heat, its friction, its strength, so that you can constantly measure what's going on.
And what's going on? Well, that's where it gets interesting, because what's going on makes the Hyperloop idea so enticing in the first place.
Almost a decade after Elon Musk brought Hyperloop into the spotlight, production is scaling up.
On this episode of Sounds Like Infrastructure, we ask if the train and plane should be worried, and find out what's needed to scale up a new infrastructure project from just a few hundred meters to almost 1,000 kilometers.
We also find out what happened in the 1840s when a system that uses some of the same technology was brought into service. Spoiler alert, it didn't go well. That's next. Hyperloop can only be a success if it offers something the car, train and plane can't offer. And that's a pretty big challenge. Today, when you want to go faster than the car can take you, you take the train or high-speed rail. When high-speed rail isn't fast enough, you take the plane. Cars for short distances, trains for medium distances, and planes for long distances. That is more or less where we stand. Hyperloop is trying to fill the gap between the train and plane, and so its niche would be between 600 and 1,000 kilometers.
We'll talk about what it's like to take a Hyperloop in just a bit, but first there's a big question of speed. How do engineers plan to take you from LA to San Francisco faster than the train or plane? Well, to do that, first you gotta solve problems of aerodynamics and friction.
Friction is developed by the air pressure on the front of the car, so aerodynamics, but also mechanical friction in terms of, the contact with the wheels and the rail and the wheels and the axles and the bearings.
Aerodynamic drag has a relationship with velocity. It has a squared relationship with velocity. So the twice as fast that you go, the 4 times more aerodynamic drag that you feel.
And this squared relationship is why high-speed trains can't really get much faster than they are today.
To solve the problem of aerodynamic drag, Hyperloop basically takes the train, gets rid of the wheels, puts it in a tube, and seals that tube.
We use that tube environment to reduce the pressure that the capsules move through. So like airplanes, the higher altitude they fly, the more efficient they are. The lower the pressure inside of our tube, up until a point, the more efficient that we are.
So it's hermetically sealed, air is pumped out. And again, there are some differences in the technologies as to how much air is pumped out and how much vacuum it is. But either way, it's very close to vacuum, and all of the technologies require that, and they need that to reduce friction, and that's what the high speeds are developed by the reduction of friction.
Surprisingly enough, the idea of using vacuums in tubes to transport people isn't actually that new.
The general concept of Hyperloop goes all the way back to the atmospheric railway and other solutions by Goddard and others going way back into the Victorian era.
Although not exactly the same as Hyperloop, Isambard Kingdom Brunel was also convinced that his atmospheric railway would change the future of transport.
And the system he built worked quite well. The trains worked well, the public liked it, and the press raved about the new invention. But then one small flaw in the system took the whole project apart.
So with the atmospheric railway, Brunel was not an innovator.
That's Colin Duval, Professor Emeritus of Railway Studies at the University of York.
The innovators were people like the Samuda brothers. Brunel, was trying to scale up something that did work at the pilot level, even worked as a small-scale operating railway, like in Ireland, to something that's much, much bigger, a main line railway, if you like. And he failed.
Brunel had proposed the atmospheric railway because the steam trains at the time didn't do hills very well. And Devon, where Brunel had planned to build his atmospheric system, was full of hills.
If you were an engineer in the 1840s faced with this problem, you only really had two choices. You could cut a route through the hill, which would instantly bring the cost up.
Or, if you wanted to use steam motive power without using a locomotive, you did have the option of using stationary engines. So every 2 or 3 miles, you would have a big stationary engine at the side of the track, and then you would connect that steam engine to a rope, and the rope would run between the rails, and you would hook your train onto the rope, and you could haul the train that way.
Although getting a second steam engine and a rope to pull your train uphill did work, it wasn't ideal. In Brunel's mind, an atmospheric railway could fix this.
The atmospheric railway promised, or seemed to promise, a new world by using what at the time was called a rope of air.
And it's this rope of air that has similarities to the Hyperloop idea. But how did Brunel plan to create his rope of air? According to Colin, like all good ideas, it's the simplicity that makes it so clever. Here's how it's done.
You place a tube between the rails, a tube with a slot in it. You place a piston inside the tube and with a rod sticking out through the slot. And you have to find a way of sealing that slot, because otherwise the next stage of this process isn't going to work. So you seal the slot with a continuous strip of leather. And once everything's nice and airtight, you use those stationary steam engines at the side of the track to pump the air out of the tube in the front of the piston. And the piston is attached to a train. And as soon as you pump the air out from the front of the tube, obviously you've got atmospheric pressure at the back, and the piston is pushed along by atmospheric pressure. It's the name, the atmospheric railway. And because the train is attached to the rod, your train whizzes along with the piston. Brilliant. The rope of air.
Just like Elon Musk today, Brunel had a reputation as an innovator. And so people listened to him when he proposed the atmospheric system for the South Devon line. But he wasn't the only one looking into it as an alternative to the steam locomotive.
The atmospheric railway wanted to improve the railway system already in place. With Hyperloop, engineers are proposing a totally new system, which has people asking, why do you need a new system in the first place? Well, the idea is not to replace the car, train, or plane, but to complement them.
If, for example, you have a route which is currently served by congested highways with no public transport, and the only other way to get from A to B in a reasonable time frame is by flying, I mean, that's a classic case where Hyperloop would provide a real alternative solution. The sweet spot for Hyperloop routes is probably, certainly at this stage of the development, is between 600 and 1,000 kilometers.
Take, for example, one of the routes Hyperloop TT has been looking into, Cleveland to Chicago. Right now, it takes 7.5 hours by public transport, 5.5 hours by car, 1 hour 10 minutes by plane. In Hyperloop,
Cleveland to Chicago in about 42 to 47 minutes, depending on the route.
And Hyperloop wouldn't just be quicker than the plane on this route, because we can design out all the things that slow us down in the airport in general. Things like security controls and actually getting to the airport itself.
It's not just the technology that has Chris excited, but also this opportunity to completely redesign the passenger experience.
You know, you think about flying and this pain of going to the airport, walking through the airport, arriving some time early, standing in a line, standing in another line, squeezing into a spot. And can't we do these kinds of things better? And do we have an opportunity to do those kinds of things better when we're sort of reimagining how all of this is happening? And I think we do.
One of the other major angles is that the flexibility of the service is significantly better than high-speed rail. So basically, a high-speed rail requires, in order to get the value, you need to have long trains that travel on a set frequency, a set timetable, because you need to manage the capacity of the rails.
Typical high-speed rail is going to hold 400 or 500 people. That means you have to find the market for 400 and 500 people to leave their destination at a particular time when the train is leaving.
The way Hyperloop is intended to work is with much smaller capsules that can be sent, obviously, very quickly, with a very short space of time in between them, down the tubes. And obviously, because the tubes are separated and they only go in one direction, they're inherently safe.
All of these things have been considered by anyone working on Hyperloop, but the next part of the project is one of the most difficult parts. And it's the part that, going back to the 1840s again, Brunel struggled with most when building his atmospheric railway.
The South Devon Railway, or proposing to use the atmospheric system on the South Devon, was scaling up to an unprecedented degree.
The atmospheric system had been proven to work at short distances of about a mile, and Brunel wasn't actually the only one attempting to scale up the system. William Cubitt, whose most famous project is probably the Crystal Palace in London, had also built a bigger atmospheric system on the London Croydon Railway.
But Brunel's project is interesting because it had a number of flaws that only became evident when the system was expanded.
When it worked very, very well. There are reliable records of atmospheric trains travelling along at 60 plus miles per hour over several miles, very quiet by comparison with the steam locomotive, lots of adulation in the press. The directors of the South Devon Railway were very pleased. So when it worked, it was very, very good. But when it didn't work, it was an absolute stinker. And unfortunately, it didn't work quite a lot of the time.
Brunel's system had a black pipe with a diameter of 63 centimeters running down the middle of the track, and on top of this pipe there was a leather seal where the piston that was attached to the train came out. To move the piston along, air was pumped out of the pipe by pumping stations, which were located every 3 or so miles along the track, and these pumping stations were just traditional steam engines in small buildings beside the track.
But as the system expanded, more stationary steam engines were needed along the track.
And it's pretty clear that Brunel miscalculated the sort of power that those steam engines had to be in order successfully to evacuate the tube. And so they were working far harder than they were designed to do, so they didn't work very economically. So right from the start, the cost of operating the stationary steam locomotives was much, much higher than anticipated.
So Brunel introduced a line of communication in the form of the electric telegraph to try to solve this problem.
And although the telegraph wasn't installed when the South Devon first opened, Brunel quickly had it installed, and that meant that the the operators could communicate to the pumping stations along the line that the train was due, so they were able to start pumping the air out of the tube, just a few minutes before the train was due to leave, rather than keeping the engines pumping away all the time and therefore wasting fuel.
But the biggest problem with the atmospheric railway wasn't these stationary steam engines. It was something else.
There was a real challenge with keeping that seal airtight. The seal on the top of the tube through which the piston poked and joined up with the train.
Is this the famous leather seal?
This is the famous or the infamous leather seal. What else could he have used? Well, I don't know. I'm not a materials scientist, but the consensus seems to be that leather was the best material available at the time.
The atmospheric railway solved the problems of Devon's Hills, but it couldn't handle the climate.
The atmosphere was very salty, extremes of rain, even snow and frost, even down there in South Devon, and also sun. So the combination of all these factors would draw the natural oils out of the leather, so that it was no longer supple, and it would crack, and then water would get into the cracks, it would freeze. As everybody knows, ice expands, so that would make the situation even worse. And so the leather seal would break down very, very quickly. No seal, impossible to create that partial vacuum in front of the piston.
So Brunel got to work again, trying to fix yet another problem on his system.
There's a tale, it might or might not be true. The rats used to eat the leather strips because they were after the tallow that was used to keep it soft.
Tallow is an animal fat that, of course, rats would love.
Whether or not that's true doesn't matter, because, again, there's reliable evidence that it was almost impossible to keep that leather supple enough.
The key issue, as we've talked about the atmospheric railway, was the use of or materials that were not up to the job, even if the actual concept was right. So the use of fat instead of, synthetic oils, for example, or the use of leather, which degraded much more quickly than, new rubber.
If Brunel had had what we have today, basically materials that can relay information about their status, the system may have actually been a success. And this is one of the advantages that Hyperloop has.
What Hyperloop is the first, shall we say, it'll be the first new public transport technology where it has been designed from the ground up and from the beginning with these technologies in mind.
Scaling up these technologies is exactly where Hyperloop TT are right now. They're now at the point where they have to show their system has moved from that first phase of development and could really work as an alternative transport model. So they're constantly having to prove the concept at different phases of the development.
Proof of concept in our strategy means that our next step for demonstrating technology is really building a full-scale commercial prototype. So we've got full-scale R&D facility in Toulouse, France. We have the full-scale tube, full-scale vacuum system. We're working in the controls that's fully integrated with the vacuum. We're working in the propulsion system. We've got propulsion tests ongoing now. We have a first capsule fuselage going now. We're doing all of that kind of integration. The limitation that we have in Toulouse with that facility is that right now our tube is about 320 meters long. It's full scale, but it's only 320 meters. So we can do a whole lot of stuff there. What we cannot do is really get up to any kind of meaningful speed with that system.
Which means now they got to make their tubes longer.
And when we go longer, we want to go longer with people. So we want to go somewhere 3 to 5, ideally a little bit longer, but 3 to 5 seems like a good sweet spot. A 3 to 5 kilometer system that carries passengers on a routine basis and really demonstrate and validate all of the commercialization potential for a Hyperloop.
Chris wants to make sure that there's a big focus on passenger experience. Stations shouldn't be too far out of the city like airports currently are.
The wait once you get to the station should only be a couple minutes.
And the experience inside the capsule should be comfortable.
Because Hyperloop capsules won't have any windows, That could include things like virtual windows.
And I think you've seen some of this technology in some of the high-end aircraft at the moment. So virtual windows. So there will be digital windows. Some are expecting the entirety of the inside of the capsule to be, a digital screen.
And ideally, the passenger experience will begin long before you get into the capsule itself.
A bigger part of that passenger experience is really how we get to the Hyperloop system, how we get into the Hyperloop system, how available that Hyperloop system is, the fact that we have very frequent departures. You're not having to get to a station an hour before because you don't want to miss the capsule, because there's another capsule that will be departing just a few minutes later. So there's no struggle to get there. Once you get there, things should be pretty frictionless and pretty seamless. And you can be directed, okay, the next capsule going to your destination is leaving from this gate, and head towards that gate and go board that capsule. And it's almost as simple as just continuing that walk through that station and getting right on board. That's really the game changer that we see in terms of the passenger experience.
There's also a wider social aspect that Hyperloop can potentially have too, not just related to the actual transport system, but as Ferrovial are looking into right now, how a city with Hyperloop might grow. And it doesn't just have to be the big name cities we already know. Take the idea of a Hyperloop in Texas, for example.
Could we drive a different type of development and equality by connecting some of the border towns or some of the less well-developed cities, and actually see a greater focus on generating equality and balance and developments in new areas rather than the perpetuation of the metroplex complex? So could, for example, Hyperloop be used to de-urbanize certain areas and actually spread people more out rather than concentrating them all in one place?
Then there's also the chance to reimagine what Hyperloop infrastructure would look like and what else it could do.
One key element of Hyperloop technology that I think is quite interesting from an urban development perspective is that if you are going to be building new infrastructure, then that infrastructure doesn't have to look like the infrastructure of old. So again, we can bring in new technologies, new ideas. So using the pillars as battery storage and energy storage, using the tubes as solar farms, using the outside of the pillars as green walls, all of this can add additional value and additional things to change the landscape of the cities and provide additional value.
And all of this potential for societal change paired with technological advances is why investment in Hyperloop continues to pour in. Unfortunately for Brunel and his atmospheric railway, their streak of bad luck meant they eventually had to pull the plug.
So they kept at it for a year or so, trying this, trying that. But in the end, even Brunel was forced to recognise that it was not going to be possible to maintain the integrity of the system at a reasonable price, and the crunch really came on the 29th of August 1848, when there was a meeting of the South Devon Railway shareholders to consider the future of the system. And Brunel himself recommended that the system be abandoned.
He recommended it be abandoned because it was too expensive to run and make all the necessary improvements for it to work efficiently.
Brunel's reputation did take a hit because a lot of money had been invested, £350,000 at the time, which today,
at a conservative estimate, that was about £40 million down the drains. And if you calculate it in a different way, you can get the figure up to something over £1 billion. So, there's a lot of uncertainty in how much it cost the South Devon's directors. But if you don't try things out, you'll never innovate.
There are still a lot of things to iron out before Hyperloop is a viable alternative to the transport we already have. Things like safety features, what happens if there's a fire in the tube, and probably the most difficult question, how do you evacuate passengers from a capsule that has an unplanned stop when the environment of the tube is like being in outer space?
And these are all questions that Chris, Adrian, and everyone involved in Hyperloop projects across the world are attempting to solve. But even with all these challenges, it's still possible we'll see a prototype from Hyperloop TT pretty soon.
Yeah. So we're in the midst of trying to close up a major fundraising round right now, which will give us that opportunity to get there. And all of our planning is showing that once that closes, we're looking at about 3 years to the commercial prototype, to being certified and welcoming you and everyone else to come visit and take a ride.
Sounds Like Infrastructure is a podcast produced by Ferrovial. Our team includes Kevin Garcia King, Candela del Valle Dominguez, Jose Luis Garcia Guaita, Teresa Bino, Arantxa Gullias Valverde, and myself, Craig Lawless.
Craig also did the edit on this episode.
You can find out more about Hyperloop and other Ferrovial projects on Facebook, Twitter, Instagram, LinkedIn, and of course, ferrovial.com.
And if you know of any engineering enthusiasts who haven't listened to the podcast yet, share an episode.
I'm Craig Lawless.
I'm Kevin Garcia King.
And this is Sounds Like Infrastructure.